Our solar system is a wonderfully ordered place, for the most part. The planets all follow a similar script when it comes to their cosmic dance. They orbit the sun on a relatively flat plane, almost like marbles rolling on a giant dinner plate. They also spin or rotate on their axes in a roughly upright position, much like spinning tops. Earth, for instance, has a gentle tilt of about 23 degrees, which gives us our pleasant, predictable seasons. Jupiter, the colossal king of our solar system, is even more upright, with a tilt of just 3 degrees. This common pattern is a leftover from the formation of our solar system, a spinning disk of gas and dust that gave birth to all the planets we know and love. This predictable cosmic ballet is what makes Uranus so utterly baffling to scientists. Uranus doesn't play by the rules, it completely ignores them. Instead of spinning upright like its planetary siblings, Uranus is tipped over on its side. Its axis of rotation is tilted by a staggering 98 degrees relative to its orbital plane. This means that Uranus essentially rolls along its orbit around the Sun. Imagine all the other planets as graceful spinning tops, while Uranus is like a barrel rolling along on its side. This extreme tilt is so dramatic that it defies all our expectations about how a planet should behave, making it the biggest oddball in our cosmic neighborhood. Why does this strange orientation capture the imagination of astronomers so profoundly? Because it hints at a violent and chaotic past, a story written in the stars that we are only just beginning to decipher. The discovery of Uranus's peculiar tilt was not a single eureka moment, but a gradual realization that unfolded over many decades. Uranus itself was the first planet discovered using a telescope, spotted by the British astronomer William Herschel on March 13, 1781. At first he thought it was a comet or a star, but its slow and steady movement across the sky revealed its true nature as a planet. For years, astronomers studied its orbit and size, but its orientation remained a complete mystery. The first clues about its strange rotation came from observations of its moons. In 1787, just a few years after discovering the planet, Herschel also found its two largest moons, Titania and Oberon. Over the following decades, more moons were discovered. Astronomers tracking their orbits noticed something very strange. Instead of circling the planet's equator in a flat plane, like the moons of Jupiter or Saturn, Uranus's moons orbited in a path that was almost perpendicular to the planet's own orbit around the Sun. Their orbits were tilted up and down, following the planet like a miniature vertical solar system. This was a massive hint that the planet itself was tilted. It was a brilliant piece of celestial detective work. Since moons are generally expected to form from a disk of material around a planet's equator, their orbital plane should match the planet's own equatorial plane. If the moons were orbiting in such a steeply inclined path, it stood to reason that the planet's equator must be tilted in the same way. The moons were acting as tracers, revealing the orientation of their parent planet. This indirect evidence was the best scientists had for over a century, a compelling but unconfirmed theory based on the strange dance of Uranus's natural satellites. The final confirmation didn't arrive until the 20th century, with the advent of more powerful telescopes and new observational techniques. By carefully analyzing the faint light reflected from Uranus, astronomers could finally measure its rotation directly. Uranus is not just unique because of its tilt, it is a truly strange and fascinating world in its own right. Located about 2.9 billion kilometers from the Sun, it is the seventh planet in our solar system and belongs to a special class of planets known as ice giants. Unlike the gas giants Jupiter and Saturn, which are mostly made of hydrogen and helium, Uranus has a much higher proportion of heavier elements. Its atmosphere is a frigid mix of hydrogen, helium, and methane, with the methane gas being responsible for its beautiful pale blue-green or cyan color. Methane absorbs red light from the Sun and reflects blue and green light back into space. Beneath its hazy, calm-looking atmosphere lies a hot, dense, and slushy interior. Scientists believe Uranus has a small rocky core at its center, surrounded by a vast, churning mantle. This mantle isn't made of molten rock like Earth's, but of a strange mixture of water, methane, and ammonia ices. Another bizarre feature of Uranus is its incredibly cold temperature. Despite being closer to the Sun than Neptune, Uranus holds the record for the coldest planetary atmosphere in the solar system, with temperatures dropping to a mind-numbing -224 degrees Celsius. Stranger still, Uranus seems to radiate very little internal heat into space, unlike the other giant planets. Jupiter, Saturn, and Neptune all emit more energy than they receive from the Sun, suggesting they have hot cores. Uranus, however, barely radiates any excess heat at all. Finally, Uranus possesses its own system of rings and moons, all of which are affected by its sideways spin. The planet has 13 known rings, which are dark and faint, made of icy particles mixed with dark radiation-processed material. It also has 28 known moons, named after characters from the works of William Shakespeare and Alexander Pope. These moons and rings orbit the planet above its equator, so they too are tipped on their side relative to the rest of the solar system. The most widely accepted and compelling explanation for Uranus's extreme tilt is known as the giant impact hypothesis. This theory proposes that very early in its history, probably more than 4 billion years ago, the young Uranus was struck by another planetary body of enormous size. This wasn't just a small asteroid or comet. Scientists believe the impactor was a massive object, perhaps 1 to 3 times the mass of the Earth. This rogue protoplanet, wandering through the chaotic outer solar system, would have slammed into Uranus not head-on, but with a glancing blow. This off-center collision would have been the key to tipping it over. Imagine hitting a spinning top with a marble. A direct hit to the center might just knock it over, but a glancing blow to its side will dramatically alter its spin, sending it wobbling and tilting in a new direction. The same principle applies to planets, but on an almost unimaginable scale. The colossal energy from the impact would have been transferred to Uranus, fundamentally changing its rotation. The collision would have been so powerful that it tilted the entire planet, along with its axis of rotation, onto its side. The impact essentially knocked Uranus over and sent it rolling along its orbital path for the rest of its existence. Furthermore, the debris from this cataclysmic collision would not have just disappeared. The shattered remains of the impactor and material ejected from Uranus itself would have formed a swirling disk of rock, ice, and gas around the planet's new tilted equator. Over millions of years, this debris disk would have slowly coalesced to form the family of moons and the faint ring system that we see today. This neatly explains why Uranus's moons and rings orbit in the same tilted plane as the planet itself. They are the children of the very same cosmic catastrophe that forever altered their parent world, a lasting legacy of a single violent day in the early solar system. When searching for evidence of a crime that happened billions of years ago, detectives must look for clues left at the scene. In the case of Uranus's great tilt, the most compelling pieces of evidence are not found on the planet itself, but in the family of moons that orbit it. The giant impact hypothesis predicts that the collision would have created a massive disk of debris, a mixture of material from the impactor and the outer layers of Uranus. This swirling cloud of gas, dust, and ice would have been centered on the planet's new tilted equator. Over millions of years, this material would have clumped together under gravity to form the moons we see today, the true children of chaos. This formation story perfectly explains the most striking feature of the Uranian system, the orbits of its major moons. All of the large moons, from Miranda to Oberon, circle the planet in a remarkably flat, orderly plane that is aligned almost perfectly with its 98-degree tilt. If the moons had existed before the impact, the cataclysm would have scattered them, sending them into wild, inclined, and eccentric orbits. The fact that they orbit so neatly in the equatorial plane is a smoking gun. It strongly suggests they were born from a debris disk that was created by the impact itself, inheriting the new sideways orientation of their parent planet from the very moment of their formation. Furthermore, the composition of these moons provides another layer of supporting evidence. They are a mixture of roughly half rock and half ice, a composition that aligns well with what we would expect from a collision between an icy giant planet and a rocky protoplanet. The moon Miranda, in particular, looks like a witness that has been through a traumatic ordeal. Its surface is a bizarre jumble of different terrains, with giant canyons, terraced layers, and smooth plains all mashed together in a chaotic patchwork. For centuries, Uranus was little more than a faint speck of light in our telescopes. The true revolution in our understanding came on January 24, 1986, when NASA's Voyager 2 spacecraft executed a historic flyby of the planet. For a brief but crucial period, humanity had a robotic emissary sending back the first ever close-up images and data from this mysterious sideways world. One of Voyager 2's most surprising discoveries was the nature of Uranus's magnetic field. Unlike Earth or Jupiter, where the magnetic field is roughly aligned with the planet's axis of rotation, Uranus's magnetic field is dramatically off-kilter. It is tilted by a staggering 59 degrees relative to the spin axis, and its center is offset from the planet's physical center by about 1/3 of the planet's radius. The flyby also gave us our first detailed look at the rings and moons, confirming their orbits and compositions with stunning precision. Voyager 2 discovered 10 new moons and 2 new rings, all orbiting within the same tilted equatorial plane. The images of the dark, narrow rings and the data on the rock ice composition of the moons provided the hard numbers that theoreticians needed to refine their impact models. The Voyager 2 encounter transformed the giant impact from a clever hypothesis into a robust scientific theory, grounded in direct observational evidence that continues to be analyzed by scientists to this day. One of the most profound and puzzling characteristics of Uranus is its temperature. It is, quite simply, unnervingly cold. The planet holds the record for the coldest measured temperature in our solar system, a frigid -224 degrees Celsius. What makes this so strange is that it radiates almost no heat from its interior. The other giant planets, Jupiter, Saturn, and Neptune, all emit significantly more energy than they receive from the Sun. This internal heat is a leftover from their formation, a primordial warmth that slowly leaks out over billions of years and helps to drive their dynamic weather systems. Uranus, however, is thermally dead by comparison. This lack of internal heat is a critical piece of evidence that strongly supports the giant impact hypothesis. A collision with an Earth-sized protoplanet would have been an event of almost unimaginable violence, depositing a catastrophic amount of energy into the young Uranus. This energy would have acted like a massive explosion, blasting away a significant portion of the planet's original primordial atmosphere. An alternative but related explanation suggests the impact didn't just vent the heat, but fundamentally rearranged the planet's interior structure. The shockwave from the collision could have churned the planet's layers, mixing heavier elements towards the outside and creating a stable, stratified layer deep within the interior. This reorganization would act like a thermal barrier, a permanent blanket trapping the remaining primordial heat deep inside the core. While observations from Voyager 2 and ground-based telescopes provide crucial circumstantial evidence, the ultimate test of the giant impact hypothesis comes from the digital world of supercomputer simulations. Scientists cannot rewind time to watch the collision happen, but they can recreate the cosmic crime scene using powerful computer models. These sophisticated models begin with a young, upright Uranus and an incoming impactor of a certain mass, speed, and angle. The computer then calculates the immense forces and energy transfers that occur during the collision. Early simulations were groundbreaking, demonstrating that a glancing blow from an Earth-sized object was indeed capable of tilting Uranus by 98 degrees. More recent simulations, benefiting from vastly increased computing power, have become far more detailed and nuanced. A 2018 study led by researchers at Durham University ran more than 50 different high-resolution impact scenarios. They found that an impact from a body about twice the mass of Earth, made mostly of rock and ice, could not only explain the tilt, but also the formation of a thin debris disk that would form the moons, and a thermal boundary that would trap heat inside the planet. These state-of-the-art simulations are the closest we can get to witnessing the ancient cataclysm. While no simulation is perfect, the remarkable success of these models in recreating the Uranian system provides the strongest evidence yet that Uranus's strange character was forged in the fires of a single colossal impact. The most dramatic consequence of Uranus's 98-degree tilt is its effect on the planet's seasons. On Earth, our modest 23-degree tilt gives us a familiar and relatively gentle cycle of spring, summer, autumn, and winter. Uranus, however, experiences seasons of an almost unimaginable extremity. With its axis lying nearly parallel to its orbital path, the planet's poles are pointed almost directly at the Sun for huge stretches of its long journey. Uranus takes 84 Earth years to complete a single orbit around the Sun. This means each of its 4 seasons lasts for a staggering 21 years. During the planet's summer solstice in one hemisphere, its pole is pointed almost directly at the Sun. For 21 long years, this entire half of the planet is bathed in continuous, unrelenting sunlight, never experiencing a moment of night. Imagine a summer day that lasts for 2 decades. While one hemisphere experiences its 21-year-long summer, the other is plunged into a winter of equal length and severity. The winter pole points directly away from the Sun, casting the entire hemisphere into 2 decades of continuous, frigid darkness. This is a polar night that lasts for a generation, a time when no sunlight touches the surface or atmosphere at all. During the equinoxes, which occur between these extreme solstices, the Sun shines directly over Uranus's equator. At these times, the planet experiences a more familiar day-night cycle, as its sideways rotation brings different regions into light and shadow over its roughly 17-hour day. This period brings about the most dynamic weather, as sunlight finally reaches regions that have been dark for decades, and regions that have been constantly lit begin to cool. This dramatic shift in solar energy triggers massive storm systems and atmospheric changes. The seasons on Uranus are not just a curiosity, they are a powerful engine driving the planet's behavior. Even though the giant impact hypothesis is our best explanation, the exact details of this ancient collision remain shrouded in mystery. Scientists have a broad strokes picture of the event, but the finer points are still a matter of intense debate and research. A key unknown is the precise nature of the object that struck Uranus. Many of the remaining questions about Uranus can only be answered by going back. The Voyager 2 flyby in 1986 was a monumental success, but it was just a fleeting snapshot. To truly understand Uranus, we need to return with a dedicated mission, an orbiter that can study the planet and its system for years, watching it through its long, strange seasons. Uranus hangs in the cold, distant darkness of our solar system as a profound and beautiful puzzle. Its serene, pale blue appearance belies a history of unimaginable violence, a story of a cataclysmic collision that forever changed its destiny. We have journeyed from the first puzzled observations of its strange, sideways dance to the modern supercomputer simulations that bring this ancient impact to life. The theory of a giant, planet-sized object delivering a glancing blow provides a powerful and elegant explanation for so many of Uranus's quirks. It accounts for its staggering 98-degree tilt, the peculiar orbits of its moons and rings, and its strangely cold, quiet nature. The evidence points to a single, transformative event that shaped an entire world. Yet for all that we have pieced together, Uranus remains a world steeped in mystery. The story is far from complete, with crucial chapters still unwritten. These lingering questions are not a sign of failure, but a beacon of future discovery. They are what make Uranus one of the most compelling targets for exploration in the 21st century. The story of Uranus is a powerful reminder that our solar system is not just a clockwork mechanism of neat, orderly orbits. It is a place with a dramatic, violent, and fascinating history. Each planet tells a different chapter of that story, and Uranus tells a tale of survival and transformation. It is the enduring enigma, the solar system's oddball, a tipped-over giant that beckons us to come closer, to look deeper, and to continue asking questions. The next great leap in our understanding is just over the horizon, promising to finally reveal the full, epic story of the sideways planet.